Continuing with our discussion of the mission and the methods of social psychology, let's look a bit at scientific theories, try and understand exactly what they are and how we test them. So what you're looking for is some kind of link between your constructs, some kind of logical link. What are your constructs? Well, for instance, the theoretical stimulus and the theoretical response. These are constructs, and you're trying to measure these constructs with the independent variable and the dependent variable. Namely, the theoretical stimulus is any particular theory you have, what does it predict if you were to manipulate that theoretical stimulus via the independent variable. So the independent variable is manipulating the theoretical stimulus. Well, we would predict, or our theory would predict, a specific response, a theoretical response. Now these are abstract and we can't see these directly, but we can measure them. We can manipulate the theoretical stimulus, and with our dependent variable, we can measure the effect it had, the theoretical response. Okay? So again, we manipulate our theoretical stimulus and we measure behavior with the dependent variable to see its theoretical response. And if the theoretical response, if the measures of the dependent variable match what the theory responded, then we believe we have confirmation of our theory. Our theory makes sense. If, on the other hand, our dependent variable suggests that the theoretical response was different than what the theoretical stimulus predicted, then we have a disconnect. See if we can understand this stuff a little bit better. So let's look at independent variables. These are observable events that causes person to do something. And so in any given experimental study, we are manipulating an independent variable in order to measure its effect with the dependent variable. This is observable behavior produced by the person. So if I introduce a stimulus to make you pay more or less attention to something, maybe my independent variable is to give you a distraction task while you're trying to do some memory experiment, for instance. So the manipulation is distraction. Are you focused or are you distracted? And I would predict that the dependent variable will indicate that your memory performance is better when you're focused than when you're distracted. Okay, so focus versus distraction is the independent variable. Your memory performance is the dependent variable. That's how we're measuring the effect of the manipulation of the independent variable. And very common in social psychology experiments are confederates. And these are people that are pretending to be participants, but are actually in cahoots with the researcher. So in contrast to a confederate, you could have a naive participant, someone who comes in, they're the actual participant. There's another person, say, that's going to be in the room that is pretending to be also a naive participant, when in fact they are actually in cahoots with the experimenter. They are a confederate. So with this understanding of variable and dependent variables, let's look at a specific theory, frustration aggression theory. That frustration leads to aggression is the basis of this theory. We don't have to know a lot about the theory at the moment. We just want to see how the theoretical stimulus and the theoretical response can be manipulated and measured with independent variables and dependent variables. Okay, so our theoretical stimulus would be frustration. We're going to induce frustration in participants. In the case of the study that's discussed in your textbook, to test this frustration aggression theory, they have, in one condition, they have somebody butt in line in front of a participant. So if you're a participant, you don't even know you are a participant. You're just waiting in line, say, at the ticket counter at the airport, and let's say you're 12th in line. Then we're going to have somebody butt in front of you, and then we're going to have the confederate. The confederate is acting like they're not part of an experiment when in fact they are. The confederate is going to rate just how frustrated you got, or really it's going to we're going to infer that frustration through the amount of aggression you show. If I butt in front of line of you, so I'm the confederate. If I butt in front of you in line and you show no response, then I'm going to mark down a 0 for that. If I butt in front of you and you show a somewhat regressive response, I'm going to put a 1 down. And then if you get really upset with me, maybe even start pushing me like, what the heck, you can't just butt in front of me in line like that, then I'm going to give that a 2. Now, the frustration regression theory suggests that if you're the 12th person in line, then your aggression is not going to be quite as strong compared to if you're the second person in line. Let's say you're just about to the ticket counter and now I butt in front of you. Not surprisingly, as I think most of us would introspect, that would make us more angry than being butt in front of when we're the 12th person in line. Having one person jump in front of you when you're 12th in line is not quite as significant as having one person jump in front of you when you're in second in line. And indeed, the results of this study show that in the high frustration condition, naive participants, are likely to show more aggression, whereas in the low frustration condition, they tend to show lower levels of aggression. So what was done in this experiment then, or what was achieved in this experiment, was manipulation of the theoretical stimulus with the independent variable, and then the theoretical response was measured with the dependent variable. So that's how it maps out. Let's look at kind of a meta-theoretical level here. What is the validity of the experiment that we just did? We can measure that validity by looking at construct validity of the cause. So the cause would be our independent variable. We would manipulate the theoretical stimulus, and that is supposed to cause the theoretical response. And so construct validity is really saying, is your independent variable causing the effect in the theoretical stimulus that you would expect? Is there a causal link between the independent variable and the theoretical stimulus? And if so, then you've got construct validity of the cause. What about construct validity of the effect? So the cause was manipulating the independent variable. The effect is going to be measured by the dependent variable, and that's going to be an effect on the theoretical response. So here we're just asking, do we have a valid measure of the theoretical response? Is our theoretical response validated by the dependent variable? Okay. So construct validity of the cause refers to the relationship between the independent variable and the theoretical stimulus. Construct validity of the effect refers to the relationship between the dependent variable and the theoretical response. And lastly, let's mention that scientific theories must be testable. What is an untestable theory? That would be a theory that can't be falsified. Okay, so falsificationism, ironically, is the basis of science, not verificationism. Turns out it's logically impossible to verify something. You can't prove something to be true, but you can disprove the truth of a theory. And so any theory that has the potential to be disproven is a scientific theory. It doesn't mean it will be disproven. If it's a true theory, then it will never be disproven. But there has to be some possible set of data that, if those data existed, would be disproof of the theory. Just to give you an example, oftentimes God theories, such as the Christian God, if you try to make that a scientific theory, it doesn't really work because you can't really test the existence of God. Any evidence you could try to produce that would suggest God does not exist, it could be argued that, well, God put those data there to test your belief, or the devil put the data there to test your belief. So, for instance, for Christian beliefs, some Christians believe that the Earth is around 6,000 years old, and contrary evidence is always given saying, well, look, we have fossils that are millions or tens of millions of years old, and radiocarbon dating suggests that the oldest rocks on the planet are 4 billion years old. How could the Earth possibly be only 6,000 years? Well, it is perfectly allowable under the God theory to say, well, but the Lord works in mysterious ways. Perhaps he put those fossils and that radiocarbon dated rocks, maybe he put those there to test your faith in him. So the point is, any data that could ever be shown that would appear to disprove either God's existence or some particular claim from the Bible, such as the Earth being 6,000 years old, if you can always say, well, sure, the data look like they disprove it, but that's just God, and the Lord works in mysterious ways, therefore we can't really know why he has put those fossils there, but he has put them there even though the Earth really is just 6,000 years old. So that theory can never be refuted. There's no data that you could ever produce that would ever say, oh, well, okay, that shows that God doesn't exist, or that shows at least that the earth must be more than 6,000 years old. So any theory that at least biblically based theory that the earth is 6,000 years old can't be tested. And if it can't be tested, then it's not a scientific theory. So what about correlational studies? We just talked about experiments, and experiments always manipulate an independent variable and measure the effect with a dependent variable. And those allow you to make inferences of causes, because if you measure an effect in the dependent variable, well, that effect had to be caused by your independent variable, at least if your independent variable has construct validity, and if your dependent variable has construct validity. But we can do non-experimental studies where we're not manipulating an independent variable, we're just measuring two variables and correlating them with each other. And in this case, you do correlational studies when you can't control variables, or you can't do random assignment. And the weakness of a correlational study is correlation does not equal causation. Okay? So correlation can tell you if there's a relationship between two variables, but it can't tell you whether one variable is causing the effect on the other variable. So correlation is a relationship between two variables. They can be positive, negative, or no correlation at all. And these are computed by correlation coefficients. And to see what these look like kind of geometrically, if you have a slope in the positive direction, then you have a positive correlation. In this case, in this theoretical set of data, all the line dots, all the sampling points fall perfectly on this regression line. And that means there's a perfect correlation for every unit you go up in X, you also go up that many units in Y. Okay? So perfect 1.0 correlation. Here is an example where the data points don't fall along any particular slope. There appears to be no real pattern in them, therefore the correlation is 0. And by contrast to a positive correlation, here we're seeing a perfect negative correlation. For every unit you go down in Y, you also go down in X. Okay. Now these are perfect correlations or zero correlation, which you don't usually get in research, especially psychological sciences. You never get perfect correlations. In fact, here's a correlation of 0.6, which is basically you could think of that as a 60% correlation versus a 100% correlation up above. Even 60% or 0.6 is a pretty rare, it's a high value. You don't usually see correlations in the psychological sciences that are that strong. Human behavior is hard to study, hard to measure, and so our correlations tend to be a bit weaker than this. But here you see it's the same idea. The slope is in a positive direction, hence it's a positive correlation. But you can see that the dots, the data, the sampling point just don't fall perfectly on that line, as they never will in real life. Okay. This is not something that actually happens. This is just theoretically what a 1.0 correlation would be. Instead, your data tend to fall distance, that as you go up in X, you go up more or less in Y. Okay. Look at the negative correlation there. As you go down in X, you go down more or less in Y. And the tighter these dots are along this regression line, the higher the correlation. Again, such that if the dots fall perfectly on that regression line, then you've got a perfect correlation. But again, not something that tends to happen in real life. Now let's talk about the fact that science is self-correcting. This is perhaps the most important feature of science. Self-correction. So important. So to compare again to, say, religious theories about the existence of the universe or what the mind is, the soul, or what have you, religious theories tend not to be self-corrective, meaning that the theory is the theory, and if you can't prove it wrong or right, the theory, then you can't correct for any theories that happen to be wrong. Again, if the God theory was a scientific theory, there would be a possible data set that, if discovered, would prove that God doesn't exist. But because of the nature of the existence of an omniscient, omnipotent being, you can't really test that theory. So it's not a scientific theory. But scientific ones, if in fact you come up with evidence that your theory is wrong, then as a good scientist, you drop that theory and you move on to the next one. Now, as humans, it can be difficult. Maybe you've invested a couple of decades of your life into your theory being correct. Well, that may mean that when you find evidence that your theory is incorrect, you may be slow to accept that. You may say, oh, well, there must have been something wrong. Let's do another experiment and see what happens. Oh, well, it must have been something wrong with those data too. Let's do another experiment. So as human scientists, we are prone to believe our theory even when it gets disproven. But fortunately, this is what makes science a community. Fortunately, you have other scientists that are going to say, man, I'm sorry, I know you want your theory to be wrong, or you want your theory to be right, but it's wrong. These data demonstrate that it's false. And most of science, even if you don't move on to the next theories, the rest of the science community will, and you'll just kind of get left behind. A good example of this was the kind of debate between Edwin Hubble and Hoyle. I can't remember Hoyle's first name, but Hubble and Hoyle. Hubble found evidence that that the universe was expanding, that other galaxies, other stars are moving away from us. Whereas Hoyle believed in the steady state theory. He believed that all the stars and all the bodies in the universe were sitting still, neither moving outward nor moving inward. But Hubble's discovery of a Doppler effect, that galaxies were redshifted, which if you know anything about the Doppler effect, that means that the galaxies have to be moving away from us. His data that he observed, this redshifting of the Doppler effect, was irrefutable proof that the universe is expanding. It disconfirmed, well, I shouldn't say irrefutable proof because we can't prove that Hubble's theory of an expanding universe was correct, but we can disprove Hoyle's theory that the universe is sitting still. If it were sitting still, then we should not have seen the redshifting of all the other galaxies. We should not have seen this Doppler effect. Doppler effect requires movement, and Hoyle's theory insists that there is no movement. Well, Hoyle apparently took a while. I don't know how many years it may have taken him, but he kept trying to save his theory. Meanwhile, the rest of science moved on, and they dropped Hoyle's theory, even though he spent years trying to save it. But eventually, being a good scientist, even Hoyle dropped his own theory. He finally was convinced that no, the steady state theory can't be correct. And so that's a real credit to Hoyle and more generally to science. Science corrects itself. If there's data that suggests you're wrong, then you change your mind. Typically in points of view, like religious points of view, it's very difficult to change one's mind. You have your book, typically your Bible, your Quran, or what have you, and it says it is supposed to be speaking the truth. And if you find evidence inconsistent with that, then according to most religions, you should refute, or not refute, but reject the evidence that the Bible is wrong or that the Quran is wrong or what have you, and maintain belief in that document, even though you apparently have evidence that it can't be correct. So science is self-correcting, and this is what makes it so incredibly valuable. This is how science can make progress. There's some issues with the psychological sciences. We rely on student samples, so the vast majority of studies in psychology, and certainly the vast majority of studies in social psychology, rely on you guys, college students. You come into our labs and we run you through experiments, and you typically get credit for some class. There are occasions where you'll pay money, or you'll be paid money rather as a subject, but most of the time it's just credit for a class that you're getting. And so reliance on student samples is difficult, and cultural relativity pops into our data unintentionally. Most social psychology is done in the West, and within the Western Hemisphere, it's really the United States that's doing the vast majority of social psychological research, which means all of our data are really just talking mostly about Americans and maybe a bit more generally about Western culture, but our data don't say a whole lot about other cultures that are not typically Western Hemisphere cultures. And so this is a bias in science that presumably can only be fixed by trying to spread the social sciences into all regions of the planet so that we're sampling from all cultures, so that the conclusions we draw generalize to the entire population, not just to folks here in the United States, as it were. All right, now let me shift from those kind of basic social psychological methods and the kind of theory behind the scientific approach. Let's progress now to talk about social neuroscience. And social neuroscience, as we mentioned before, came into being in the last 10 to 15 years, somewhere around the early 2000s to about 2010 is when that term social neuroscience really first came into use. And social neuroscience became a thing once brain imaging techniques were applied to testing social psychological theories, hence social neuroscience. And I'm just going to mention two of the most common tools used in social neuroscience. One is EEG, or electroencephalography. And here we're using this cap with a bunch of electrodes. We're measuring the electrical activity on the encephalon. And the encephalon just means head. And you can see that these electrodes are just sitting on the head, on the scalp. Okay. So again, graphis is for record, like photography. But instead of recording photons, we're recording electrical signals. Where are those electrical signals coming from? The encephalon, hence electroencephalography, EEG. And, EEG has excellent temporal resolution. This system here, along with the amplifier, you can't see the amplifier back behind the subject, but there's an amplifier, and then that amplifier is sending the electrical signals from your brain, it's sending them to record on the hard drive of a computer that it's hooked up to. And this system can sample that electrical activity every bit as fast as the electrical activity is happening. So we have excellent temporal resolution. Be quiet. We have poor spatial resolution, however. Even though we can tell you when the brain activity is happening, it's very difficult to say where in the brain that activity is coming from. It's not impossible, but it is extremely difficult, and it's difficult to know whether you have the right answer when you do it or not. So many psychologists just use the temporal information. That is, they say when brain activity occurs, but they don't tend to say that it happened in the hippocampus or in the prefrontal cortex. They tend not to specify the location in the brain because our resolution of location or resolution of space is very low. So how can this stuff be used to measure social psychological processes? Well, this image comes from a study in which participants were asked to look at faces of white men and faces of black men. And for each face they saw, they were to indicate, would I like to work with this person or not? We will likely talk about this study right at the very end of this course when we discuss racism and prejudice. So I don't want to give you too many details right now. The focus here is not so much on what they studied as much as how you can use EEG to study social neuroscience questions. So in this case, they're running a bunch of white male participants. They're rating each of these white and black faces. There's going to be probably 100 of white ones, 100 black ones. And for each one, they're just supposed to look at the face and say, do you think you'd like to work with this guy? Now, these images are a little misleading because it suggests that the white guys have this really jerky look on their face, whereas the black guys have nice, pleasant smiles. Well, for every nice, pleasant smile you have in a picture of a black man, there's going to be a picture of a white man that has a nice, pleasant smile. Every picture of a white man where he kind of looks like he wants to beat you up, there's going to be a picture of a black guy that looks like he wants to beat you up. So the emotions expressed are going to be balanced. So don't if you're a good scientist in the making, then you'd probably say, well, wait a minute, these faces look less pleasant than these faces. Okay, well, that's just because of the pictures the researchers happen to use to show you how this paradigm works. So you're basically going to say, would I like to work with this guy? Would I like to work with this guy? You're going to do that times 100 of each of those stimuli. And according to this theory, people who scored low in racist behavior, they're going to predict they're going to have more brain activity. The idea is that the average white guy, even if he's not explicitly racist toward black people, he may nonetheless show strong brain activity, suggesting that prejudicial ideas may pop in the white participant's head when he sees the black participant, but he actively works to inhibit that brain activity. So it takes more brain activity to inhibit the prejudicial beliefs if you're low in racism. So just to finish explaining the data, the bold line here are participants that were very overtly racist. They said, "No, I don't want to work with a black guy. I will work with a white guy." So the people who were overtly racist, they showed less brain activity than the people who were not racist. The people who said, "No, I'm as equally likely to want to work with a black guy as I am to work with a white guy," well, their brain activity is this thin line, the one that shows more brain activity, suggesting that the difference between them and racist is probably not that the guys who were equally likely to say black or white, not that they have no prejudicial beliefs, but rather they actively work to inhibit their prejudicial beliefs. Again, it's a lot to ask you to understand this research right here in this early phase of the game. I'm not so much trying to point out to you or trying to get you to understand the details of the study as much as to show you that we can collect brain data that can tell us, are people that are low in racism, are they low in prejudice, or do they have prejudice and just actively work to inhibit those prejudices? So again, we'll discuss this experiment later, as we will this functional magnetic resonance imaging study. Okay, so we're all familiar with MRI. Perhaps a few of us are familiar with functional MRI. Same machine, this electromagnet here. You're going to slide the person's body into this magnetic field, and you're going to measure the effect of their brain on that magnetic field. And what you can get is something called the blood oxygen level dependent signal, or the BOLD signal. Now, this acronym really makes more sense backward. This is a signal that's dependent on the level of oxygen in the blood, but of course, DLOB isn't as easy to remember as BOLD, so they call it the BOLD signal. And basically, it just turns out that oxygenated blood affects the magnetic field differently than deoxygenated blood. Why does that matter? Well, because if you're going to use, say, as we see here, the left parietal cortex is showing a BOLD response, that means that there's been a change in the amount of oxygen in the neurons in that brain region. And if the amount of oxygen has changed, that's because those neurons fired. So we can see which neurons in the brain are firing based on where the changes in oxygen have occurred. Okay? And for that reason, we have excellent spatial resolution with fMRI. Of all the tools out there, certainly more than EEG or any of the other tools, functional MRI gives you the most detailed information about where brain activity is occurring. However, it has very poor temporal resolution because the blood flow response is so slow in the body. You know, neurons activate in about 100 milliseconds, whereas blood flow happens across about 12 seconds. So the temporal resolution of fMRI is very slow because it's not measuring brain activity, it's measuring blood flow. But that blood flow is very strongly correlated to brain activity. Therefore, we know that if the fMRI machine tells us it came from this location, we know that that's the location it came from. However, we don't know exactly when that brain activity occurred. So EEG has excellent temporal resolution but poor spatial. fMRI has poor temporal but excellent spatial. Just the opposite of each other. Therefore, they're kind of complementary tools. And sometimes the tools get used together, although most people, for very technical reasons, don't use them together. They use them separately, typically. And just to show you how fMRI can be used to look at social psychological issues, well, this study is looking at mirror neurons. So here we have in the left inferior frontal cortex, we have a region of activity that's believed to be mirror neurons, although the truth is the researchers here really can't say whether this is mirror neuron activity for sure or not. Whatever the case, this activity they believe to be mirror neurons does show significant positive correlation with an empathy questionnaire. So if you give the participants that went into the MRI scanner, you also are going to have them fill out an empathy questionnaire. And those that score higher in empathy, so we see here balanced emotional empathy scale, that's the questionnaire score. If you're up here toward the top of the empathy questionnaire, you have high empathy ability. Well, that means you also have a strong BOLD response in this brain region. Okay, so if you have low relative empathy scores, then it turns out you have low amounts of bold response in this brain region. Therefore, this is a positive correlation between a person's self-reported empathy, as measured by the questionnaire, and the amount of brain activity they get as measured by functional MRI. So again, it's over the last couple of decades that social psychologists have gotten hip to these cognitive neuroscience techniques, brain imaging techniques like functional magnetic resonance imaging and electroencephalography. And in these last couple of decades, as social psychologists have tested their theories on prejudice, or their theories about empathy, or their theories about self-identity, or their theories about aggression, etc., as they've applied these brain imaging techniques to those social psychological science experiments, we have had the advent of social neuroscience.